Niels Bohr entered the world of physics at a moment when science was truly standing at a crossroads. The atom, once thought to be the smallest indivisible particle of nature, had already begun to reveal a deeper and more complicated structure. Electrons had been discovered. The nucleus had been identified. Yet despite these breakthroughs, the atom remained a puzzle, a riddle with pieces that refused to fit together. Classical physics could describe planets circling stars and describe projectiles arcing through the air, but it could not explain why atoms did not collapse, why the negatively charged electrons did not fall into the positively charged nucleus, or why different elements produced unique colors when heated. Into this swirling mix of confusion and scientific frustration stepped Niels Bohr, a young physicist from Denmark with a mind sharp enough to question the foundations of physics and an imagination bold enough to rebuild them. Before Bohr, the atomic model was little more than educated guesswork. J. Thomson imagined the atom as a plum pudding, with electrons floating in a sphere of positive charge. This model failed to explain almost everything important about atomic behavior. Then came Ernest Rutherford, who showed through his famous gold foil experiment that almost all of an atom's mass was concentrated in a tiny nucleus at the center. His model introduced the idea of electrons orbiting that nucleus like planets around the sun. But even Rutherford's atomic picture created new problems. Classical physics insisted that any charged particle moving in a circular path must emit energy continuously. If electrons behaved like that, they should radiate energy, spiral inward, and collapse into the nucleus in a fraction of a second. Yet real atoms were stable. Their electrons did not crash inward. They remained intact, producing predictable patterns of light. Rutherford's model was brilliant, but incomplete. He had uncovered the structure of the atom, but he could not explain its behavior. Bohr saw clearly what others had not yet dared to see. The old rules of physics simply did not apply inside the atom. The world of the very small required new principles, new ideas, new mathematics, and even a new way of thinking about nature itself. When Bohr began developing his theory, he studied the mysterious spectrum of hydrogen, a simple atom with one proton and one electron, yet capable of producing a beautiful sequence of colored lines. When energized, these spectral lines were like fingerprints, unique to each element. Scientists could observe them, measure them, and record their precise wavelengths, but they could not explain why hydrogen emitted only specific colors instead of a continuous rainbow. Bohr understood that this mystery was the key to deciphering atomic structure. If he could explain why hydrogen emitted only certain frequencies of light, he could reveal the fundamental rules governing electrons inside atoms. His breakthrough came when he combined Rutherford's nuclear model with Max Planck's revolutionary idea of quantization, the idea that energy is not infinitely divisible, but instead comes in discrete chunks. Bohr proposed something astonishing. Electrons could orbit the nucleus only at certain specific distances, corresponding to fixed energy levels. They were not free to move anywhere they pleased. They could not spiral inward or drift outward continuously. Instead, they had to remain in one allowed orbit unless they absorbed or released a precise amount of energy. When an electron leaped from one orbit to another, it did so instantaneously, without traveling through the space in between. This wasn't a smooth, classical movement. It was a quantum jump, the beginning of a new era of physics. To understand how radical this idea was, imagine telling astronomers that planets can orbit the sun only at certain fixed distances, and that Earth could suddenly jump to Mars's orbit if it absorbed the right amount of energy. In the macroscopic world, such behavior would seem impossible, but Bohr recognized that the atomic world was governed by different laws. By quantizing the electron's orbit, he solved the problem that had defeated classical physics. Because electrons were restricted to specific orbits, they no longer lost energy continuously. They remained stable, the atom endured, and the mysterious spectral lines of hydrogen suddenly made perfect sense. Each color of light emitted by hydrogen represented a unique transition from one orbit to another. The precise wavelengths matched Bohr's calculations exactly. Bohr's model may seem simple now, almost like a neat illustration in a school textbook, but at the time it was nothing short of revolutionary. It took courage to propose a model that contradicted centuries of scientific thought, yet Bohr did so with the confidence of someone who saw nature more clearly than those around him. He was not merely guessing. He used mathematics, experimental evidence, and deep physical intuition to construct a picture that explained what no previous model could. His atom resembled a tiny solar system, but one governed by strict quantum rules that dictated where electrons could and could not exist. This idea opened the door to a new understanding of matter itself. The true power of Bohr's theory became undeniable when scientists applied it not just to hydrogen, but to many other atoms and molecules. It provided a foundation upon which future quantum theories could be built. His model showed that electrons behave neither like classical particles nor like smooth, predictable waves. They exist in stable orbits defined by quantum numbers, and their interactions with light are governed by discrete energy differences. These ideas eventually gave birth to the more sophisticated quantum mechanics developed by Heisenberg and Schrödinger. But none of that would have been possible without Bohr's initial leap into the unknown. The documentary story of Bohr's planetary model is also the story of how science evolves. The history of physics is filled with moments of brilliance, but Bohr's achievement stands among the most significant because it transformed not only atomic physics, but the very philosophy of science. He showed that the universe behaves differently at different scales, and that our ordinary intuition, shaped by everyday experience, cannot always be trusted. His model gave scientists permission to think differently, to imagine systems that defied classical logic, and to explore a realm where energy levels were discrete, motion occurred in jumps, and the boundaries of knowledge were limited only by imagination. Bohr's planetary model also played a crucial role in guiding future experiments. By predicting precise energy levels, it motivated spectroscopists to investigate atomic transitions more carefully. It guided chemists in understanding why elements form certain bonds and not others. It influenced technology from lasers to semiconductors. It shaped the development of nuclear physics, leading eventually to the discovery of fission. Even in modern quantum mechanics, where electrons are described not as orbiting particles, but as probability clouds, the central idea of quantized energy levels remains directly inherited from Bohr. In a sense, his planetary model lives on inside every quantum equation used today. The human element of this story is just as compelling. Bohr was known for deep thinking, intense focus, and a gentle, almost humble personality. Yet, when he believed in an idea, he pursued it with a quiet determination that often surpassed the boldness of his more outwardly confident peers. He was not afraid to challenge scientific authority because he understood that truth often appears first as a contradiction. His approach to science emphasized collaboration, open discussion, and the exchange of ideas. His Copenhagen Institute later became a global center for theoretical physics, but its foundation rested on the same principles that guided his planetary model: curiosity, questioning, and willingness to rethink the universe from the ground up. Bohr's revolution was not merely scientific, it was conceptual. He forced the world to confront a new kind of reality, one in which certainty gave way to probability, and deterministic laws gave way to quantum rules. His planetary model acted as a bridge between the familiar world of classical physics and the strange, counterintuitive world of quantum mechanics. Without that bridge, the later developments of quantum theory might never have been possible. Understanding the atomic structure is not just an academic exercise. Every atom in the universe, every star, every molecule, every living cell follows the rules that Bohr helped uncover. The stability of matter, the colors we see, the chemical reactions that sustain life, the electronics that power modern technology, all depend on the quantized energy levels predicted by Bohr's planetary model. Even if modern quantum mechanics has moved beyond the image of electrons orbiting in fixed paths, the underlying principle of quantization remains a pillar of physics. Bohr's model also represented a triumph of imagination. At a time when many scientists were still trying to explain the atom through classical means, Bohr dared to propose something wholly new. He treated the quantum as a fundamental aspect of reality, not an inconvenient mathematical trick. By doing so, he helped create a new scientific language, a language capable of describing the universe at its most fundamental level. That language has become the foundation of everything from quantum computing to particle physics. The story of Bohr's planetary model teaches us that progress comes not only from observation, but from insight. Bohr did not simply record data, he interpreted it. He saw patterns where others saw confusion. He recognized that the puzzle of atomic spectra was not an obstacle but a clue, a doorway into a deeper understanding of matter. His theory transformed obscure spectral lines into a roadmap of the atom's internal architecture. Even today, when students first learn about the atom, they often begin with Bohr's model. It remains an iconic representation of atomic structure, not because it is the final word, but because it captures the essence of a scientific revolution. It shows that science is not static, models evolve, theories mature, but each new idea builds upon the foundation laid by the breakthroughs of the past. Bohr's planetary model is one such breakthrough, an elegant, daring, and profoundly influential step toward understanding the quantum universe. His achievement continues to inspire. It reminds us that the universe is stranger and more beautiful than our everyday experience reveals. It reminds us that questioning assumptions can lead to discoveries that change everything. And above all, it reminds us that even the smallest building blocks of nature are governed by rules that require imagination, creativity, and courage to uncover. Niels Bohr provided that courage. His planetary model gave humanity a new way to see the atom, and in doing so, a new way to understand the universe. The deeper one looks into the story of Niels Bohr's planetary model, the more one realizes how profoundly it reshaped not only physics, but the way humanity thinks about the universe. After Bohr proposed that electrons could occupy only certain fixed orbits around the nucleus, the scientific world did not immediately accept his ideas. Many found the concept strange, even unsettling. How could an electron simply jump from one orbit to another without ever passing through the space between them? How could nature behave in such discrete, abrupt steps when everything in the macroscopic world seemed smooth and continuous? But Bohr understood that the atomic world was not obligated to behave in ways familiar to human experience. The atom was a domain untouched by intuition, and if the laws there were strange, then it was the responsibility of science to widen its imagination. Early criticisms only strengthened Bohr's resolve. He refined his equations, clarified his assumptions, and showed that his model was not just a convenient illustration, but a powerful predictive tool. His calculations matched experimental results with astonishing precision. This accuracy forced even skeptical physicists to take notice. The spectral lines of hydrogen, which had once been a bewildering series of colors, now became confirmation points for Bohr's theory. Every transition between his predicted orbits corresponded exactly to an observed wavelength of light. Nature itself seemed to be validating Bohr's vision. Still, Bohr was not satisfied with merely explaining hydrogen. He sensed that if the atom could be understood through quantized orbits, then perhaps the entire periodic table could eventually be explained by quantum rules. This dream motivated him to push his theory further, even as it became clear that more complex atoms required more sophisticated mathematics. But the seed had been planted. Physicists everywhere now had a guiding principle. Electrons exist in allowed energy levels, and these levels determine the chemical and physical properties of matter. This idea soon became the unifying theme of atomic physics. What makes the story even more remarkable is the intellectual environment in which Bohr worked. Physics in the early 20th century was undergoing a dramatic transformation. Max Planck had introduced the quantum concept. Albert Einstein had used quantization to explain the photoelectric effect, yet neither Planck nor Einstein had attempted to redesign the atom itself. Bohr's contribution was unique because he applied quantum ideas directly to atomic structure, something no one else had dared to do. His model became the first true quantum theory of matter, a bridge between the experimental discoveries of the 19th century and the theoretical revolutions that were still to come. One of the most compelling aspects of Bohr's story is how he combined bold intuition with a deep respect for experimental fact. He did not build his theory from imagination alone. Every element of his model had to satisfy a physical requirement. Why were orbits quantized? Because without quantization, atoms would collapse. Why did electrons remain stable? Because only specific orbits prevented continuous radiation. Why were spectral lines discrete? Because energy differences between orbits were discrete. Bohr understood that the universe was delivering clues through observation. His genius was recognizing those clues as pieces of a larger pattern. As Bohr's ideas gained acceptance, they began influencing fields far beyond atomic theory. The concept of quantized orbits inspired new lines of research in chemistry, helping explain why elements combine in certain ratios and why some atoms are more reactive than others. His model created a framework for understanding chemical valence, ionic bonds, covalent bonds, and the periodic behavior of the elements. The periodic table, once an empirical arrangement of atomic masses and properties, now had a quantum explanation rooted in electron structure. This was a profound transformation. Suddenly, the order of the elements was no longer a mystery, but a reflection of quantized electron shells. Bohr's work also influenced the growing field of nuclear physics. If electrons were arranged in stable orbits, might the nucleus also have its own structure governed by quantum rules? This question motivated researchers to investigate nuclear energy levels and particle interactions. Although Bohr himself later contributed to nuclear research, including early theoretical work on fission, the origins of this exploration can be traced back to his atomic model. His insights into quantized systems encouraged physicists to consider quantization as a universal principle, not a mathematical trick. Despite the success of his model, Bohr was always aware of its limitations. He recognized that electrons could not truly be viewed as tiny planets orbiting a miniature sun. The planetary analogy was useful for visualization, but the reality was far stranger. Electrons behaved both like particles and like waves. Their positions could not be known with infinite precision. Their motion could not be described by classical trajectories. Bohr understood this intuitively, even before Heisenberg formulated the uncertainty principle. He recognized that his model was a stepping stone, a necessary stage in the evolution of quantum theory, but not the final word. This humility allowed Bohr to remain open to new ideas. When Werner Heisenberg developed matrix mechanics, Bohr immediately recognized its significance and helped refine it. When Erwin Schrödinger introduced wave mechanics, Bohr again saw its potential, even while challenging certain interpretations. Bohr's willingness to collaborate and debate became a lifelong hallmark. His institute in Copenhagen became a hub of quantum research, attracting the brightest young physicists from around the world. These individuals brought their own insights, but they also absorbed Bohr's gentle but rigorous style of inquiry, one that emphasized clarity, dialogue, and conceptual understanding. The documentary narrative of this period would show Bohr walking through the halls of his institute, deep in conversation with students, discussing equations on chalkboards, and exploring the philosophical implications of quantum mechanics. He believed that science was not only about predicting results, but about understanding the meaning behind those results. This mindset led him to formulate his famous principle of complementarity, the idea that nature can exhibit seemingly contradictory behaviors that are both true, depending on how one observes the system. This principle would reshape quantum mechanics and become one of its defining philosophical pillars. But the roots of complementarity can be traced back to the very first moment. Bohr embraced quantum jumps moments where the classical picture no longer made sense, yet the quantum description revealed a deeper truth. As quantum mechanics matured, some scientists believed that Bohr's planetary model had become obsolete. Strictly speaking, this was true. Modern quantum mechanics replaced Bohr's orbits with orbitals probability clouds describing where electrons are likely to be found. But despite this replacement, the influence of Bohr's original model never disappeared. It remained a conceptual guide, a stepping stone that allowed the world to transition from classical thinking to quantum reasoning. And in educational contexts, it continues to serve as the first intuitive picture of atomic structure that students encounter. The reason is simple. It captures the essence of quantization in a way the mind can grasp. Bohr's model also holds historical significance because it demonstrated the power of blending theory with experimentation. His calculations were not abstract speculations. They matched what scientists had measured in laboratories. This alignment between theory and evidence became a standard for future models in physics. Any new theory had to not only make sense mathematically, but also correspond with observable reality. This approach continues to shape scientific methodology today. The profound impact of Bohr's model extended into the technological world as well. By unlocking the quantum behavior of electrons, Bohr laid the groundwork for modern electronics, from transistors to lasers. The semiconductor industry, the foundation of computers and communication technology, relies on quantum principles that trace their origin to the energy levels Bohr described. The precise control of electron transitions in lasers stems directly from the concept of quantized states. Even magnetic resonance imaging, LED lights, and solar cells owe part of their theoretical foundation to Bohr's earliest quantum ideas. The world we live in today, digital, interconnected, technologically advanced, stands on the pillars Bohr helped build. The story of Bohr's planetary model is also a story of human creativity. It illustrates how breakthroughs occur not only through logical analysis, but also through deep intuition. Bohr trusted his instincts even when they led him into territory that defied conventional wisdom. His willingness to question deeply entrenched ideas made it possible for him to see patterns hidden from others. This trait is often overlooked but essential to scientific progress. Breakthroughs arise not from following established paths, but from daring to carve new ones. In reflecting on Bohr's achievement, one must also consider the cultural and historical context. The early 20th century was a period of extraordinary global change, technological, political, and intellectual. Old empires were crumbling, new ideologies were emerging. The arts were redefining themselves through bold, abstract movements. Science, too, was reinventing itself. Bohr's quantum ideas mirrored the era's spirit of transformation, challenging traditional views and urging the world to rethink its understanding of reality. His model symbolized a shift toward uncertainty, probability, and duality concepts that resonated with the evolving philosophical climate of the time. Yet, despite the revolutionary nature of his work, Bohr himself remained modest. Those who knew him often described him as gentle, thoughtful, and deeply reflective. He was not concerned with fame or recognition. He cared about the pursuit of truth and about nurturing the next generation of thinkers. His influence extended far beyond his scientific papers. It lived in his conversations, in his teaching methods, and in the intellectual culture he fostered at his institute. Bohr's planetary model, though eventually surpassed by more advanced theories, remains a shining example of how a single idea can change the trajectory of human knowledge. It demonstrated that the atom is not a miniature version of the solar system, but a quantum structure governed by rules that defy classical logic. It paved the way for a deeper understanding of matter, energy, and the fundamental forces of nature. It helped unlock the mysteries of the periodic table, the structure of molecules, and the behavior of light. And it laid the foundation for technologies that would transform the modern world. To appreciate the magnitude of Bohr's contribution, imagine a universe where his model was never proposed. The spectral lines of hydrogen might still be a mystery. The periodic table might lack a theoretical foundation. The notion of quantized energy levels might remain unrecognized. Quantum mechanics might have emerged much later, perhaps in a different form. The technologies that depend on quantum principles, computers, lasers, MRI machines, photovoltaics, might have been delayed by decades. Bohr's work accelerated scientific progress in ways that ripple through every area of modern life. The documentary story of his planetary model is therefore not just a scientific tale, but a story about imagination, courage, and the power of questioning what others accept as truth. It shows that progress often comes from those who dare to see differently, who reach into the unknown and return with insights that reshape the world. Bohr did exactly that. He looked at the atom and refused to believe that classical physics held all the answers. He embraced the quantum long before most of his contemporaries even understood its implications. He saw stability where others saw collapse, order where others saw chaos, and structure where others saw mystery. Even now, more than a century after Bohr introduced his planetary model, its influence endures. Scientists still refer to energy levels, orbitals, transitions, and quantum jumps, concepts directly descended from Bohr's original insight. His work remains a cornerstone of physics education, and a symbol of the moment when humanity first glimpsed the quantum world. It marks the beginning of a scientific revolution that continues to unfold today, as researchers explore quantum computing, quantum communication, and the fundamental nature of particles. Niels Bohr's planetary model did more than revolutionize atomic structure. It opened the door to a new universe, one where certainty dissolved into probability, where particles became waves, and where energy came in discrete packets. It challenged humanity to expand its understanding of nature and embrace a deeper, more complex reality. Bohr's achievement is a testament to the power of human thought, a reminder that the universe is far more intricate than it first appears, and a celebration of the moment when science took its first bold step into the quantum age. When scientists of the early 20th century looked at the atom, they saw a problem far bigger than anything classical physics could solve. For generations, physics had been built on the belief that nature flowed continuously. Motion was continuous. Energy changed continuously. Light radiated continuously. Everything in the universe, from planets to pendulums, behaved in a smooth, uninterrupted way. But when researchers studied atoms, especially the way they emitted and absorbed light, they found patterns that made no sense in this classical world. Atoms did not radiate all colors of light. Instead, they produced sharp, discrete spectral lines, as if nature were choosing only certain frequencies and rejecting others. This mystery lingered for years until Niels Bohr introduced an idea that would break the foundations of classical thinking. Electrons do not move smoothly when they change energy. They make quantum jumps, sudden, discontinuous transitions between fixed energy levels. This idea was not only revolutionary, it was unsettling. It forced physicists to confront a truth that seemed to contradict every instinct shaped by everyday experience. Bohr's concept of quantum jumps emerged from a profound realization that the atomic world does not operate like the macroscopic world. Classical physics insisted that energy could vary gradually, but the evidence inside the atom argued otherwise. When scientists observed the hydrogen spectrum, they found that hydrogen emitted only certain specific colors, each corresponding to a very precise frequency. These frequencies were not random, nor were they part of a smooth continuum. They formed a pattern distinct, repeatable, and sharply defined. This meant that the atom could not be radiating energy continuously. Something within the atom was selecting these frequencies, like a musician choosing which notes to play on an instrument. But unlike an instrument, the atom was limited to specific notes only. The question was why. Bohr understood that these mysterious patterns could not be explained by the idea of electrons moving freely around the nucleus. In a classical picture, an electron moving in a circular orbit should radiate energy constantly, losing speed and spiraling inward. But real atoms did not behave this way. They were stable, they remained intact, and the frequencies of light they emitted followed mathematical patterns. Bohr recognized that the key lay in Planck's quantum hypothesis, the idea that energy comes in discrete packets rather than continuous amounts. But Bohr took this idea much further. He applied it directly to the motion of electrons inside the atom, claiming that electrons could not possess just any energy. They were allowed only certain fixed energy values. These values corresponded to orbital positions, and electrons were forbidden from occupying anything in between. This led to the most striking part of Bohr's theory. Electrons do not gradually drift from one orbit to another. They leap, they jump. They transition abruptly between one allowed energy state and another, emitting or absorbing a precise amount of energy equal to the difference between those two levels. These were quantum jumps, a concept that defied the continuous world view of classical mechanics. To Bohr, the quantum jump was not merely a phenomenon. It was a fundamental rule governing the atomic universe. It explained why atoms emit discrete spectral lines. When an electron drops from a higher energy orbit to a lower one, it releases a packet of light whose frequency corresponds exactly to that energy difference. This alignment between theory and observation gave Bohr's model extraordinary predictive power. Suddenly, the strange, fragmented spectra of hydrogen made perfect sense. Yet even with this success, the idea of quantum jumps was deeply troubling to many physicists. The notion that electrons could change energy without passing through intermediate states seemed almost magical. How could a particle simply vanish from one orbit and reappear in another? How could nature be discontinuous at its most fundamental levels? Bohr argued that the problem was not with nature, but with human assumptions. The atom was not required to obey the smooth continuity of classical physics. The atomic world followed quantum rules that were different, rules that required imagination to grasp, rules that would force humanity to rethink the meaning of motion, energy, and even reality. Despite the discomfort quantum jumps caused, Bohr insisted that they were essential to the structure of the atom. Without them, atomic stability could not be explained. The concept of quantized energy levels prevented electrons from radiating energy continuously. It allowed them to occupy stable orbits indefinitely, and when they did transition, the process was governed by strict quantization, ensuring that every electron jump produced a specific, predictable frequency of light. This precision was what made atomic spectra so clean and orderly. Even physicists who doubted Bohr's model could not ignore that his equations matched experimental results with remarkable accuracy. The documentary narrative of this period would show Bohr staring at the chalkboard in his Copenhagen office, surrounded by notes, diagrams, and spectral data. It would show him pacing thoughtfully, contemplating the strange idea that electrons behave in abrupt leaps instead of smooth curves. It would show him discussing these ideas with young physicists, future giants like Heisenberg, Pauli, and Dirac-Meniov, whom were at first skeptical but eventually recognized the profound truth behind Bohr's thinking. These quantum jumps were the beginning of a new scientific era. Bohr's work also revealed something deeper. The universe contains structure even in its smallest scales. The atom is not a random swirl of particles, but a system governed by quantized rules. Without discrete energy levels, the universe would look entirely different. Atoms would collapse, molecules would not form, chemical reactions would not occur, and the world as we know it could not exist. Quantum jumps allow atoms to absorb and release energy in controlled amounts. They enable matter to remain stable. They shape the behavior of everything, from the colors in a flame to the light of distant stars. Whenever we see neon signs glowing, lasers cutting through metal, or LED illuminating a room, we are witnessing the direct consequences of Bohr's quantum jumps. Even though later developments in quantum mechanics replaced Bohr's orbits with probability distributions and wave functions, the concept of discrete energy levels never disappeared. It remained fundamental. Modern quantum mechanics describes electrons not as particles hopping between circular paths, but as wave-like entities occupying quantized states. Yet, regardless of the mathematical framework, the idea of fixed energy levels and instantaneous transitions persists at the heart of the theory. Bohr's quantum jumps became the foundation upon which quantum mechanics was built. This idea has also shaped modern technology. Lasers operate because electrons jump between specific energy levels, releasing coherent light in the process. Semiconductor devices, transistors, diodes, and integrated circuits rely on quantized energy bands. Solar cells convert sunlight into electricity by promoting electrons across quantized energy gaps. Even atomic clocks, the most precise timekeeping devices ever invented, operate by measuring the frequency of quantum jumps in atoms. The entire digital world rests on the principle Bohr introduced. Beyond technology, quantum jumps have influenced the philosophical understanding of nature. The concept shattered the assumption of continuity and forced scientists to consider a world made not of smooth flows but discrete events. It introduced the idea that physical systems do not always evolve gradually, but sometimes change in abrupt steps. This challenged classical determinism and opened debates about the role of measurement, observation, and probability in physics. Bohr's insistence that quantum jumps were real initiated discussions that still continue today. One of the most profound aspects of Bohr's contribution is that he recognized quantum jumps not merely as mathematical formalities, but as physical events with deep meaning. He understood that they represented a shift in how humanity perceives the universe. The world was no longer a clockwork machine ticking smoothly along. Instead, it was a realm of quantized energies, probabilistic outcomes, and sudden transitions. Bohr saw the atom not as a miniature replica of the solar system, but as a stage where nature performed in discrete steps. This understanding required courage. Many physicists were uncomfortable with the idea that electrons could disappear from one orbit and reappear in another without traveling through space in between. But Bohr saw beyond this discomfort. He knew that these jumps were necessary to explain atomic stability. He embraced the quantum because he understood that nature itself demanded it. This acceptance paved the way for Heisenberg's uncertainty principle, Schrödinger's wave mechanics, and the full development of modern quantum theory. Bohr's quantum jumps also provided a new language for describing the microscopic world. Before Bohr, physicists spoke of continuous energies, orbits, and forces. After Bohr, they spoke of states, transitions, and quanta. This shift in language reflected a deeper shift in understanding. The atom was no longer a classical object. It was a quantum system governed by rules that could not be visualized in ordinary space and time. The more scientists studied quantum jumps, the more their importance became clear. The jumps revealed that energy is conserved in precise amounts. They demonstrated that matter interacts with radiation in quantized exchanges. They helped explain why atoms emit light when heated, why chemical reactions release energy in specific steps, and why the universe has structure. Every time an electron jumps, it participates in a process that shapes the behavior of matter on every scale. Bohr's insight into quantum jumps was therefore more than a scientific discovery. It was a transformation of human thought. It showed that the universe at its core is built not from smooth motion, but from discrete, sudden changes. It revealed that nature is not continuous but quantized, and it provided the first clear picture of how atoms behave, opening the door to all future quantum research. As the story of quantum physics continued to unfold through the early 20th century, Niels Bohr's idea of discrete energy levels had already begun to ripple through every laboratory, every scientific meeting, and every debate that dared to question how the natural world truly functioned. Yet the deeper the scientific community looked into the atom, the more astonishing it became that such a simple sounding idea could carry so much force. Bohr had insisted that electrons existed in specific states rather than roaming freely, and he described their transitions as abrupt, discontinuous jumps, things that seemed too strange to fit comfortably within the smooth fabric of classical physics. The world of Newton, Maxwell, and Einstein felt precise and predictable, but Bohr was now revealing a domain where nature behaved in leaps, steps, packets, and sudden bursts. It was as though reality had hidden a secret rhythm that no one had noticed, a rhythm that only Bohr's insight could begin to illuminate. Physicists who initially resisted Bohr's model soon found themselves drawn into its logic. Experiments kept supporting the idea of discrete transitions, and this forced many to rethink long-held beliefs. For decades, scientists assumed energy was continuous, like water flowing through a stream. Bohr showed them that under the surface, the stream was actually made of droplets. And in this microscopic dance of matter and energy, electrons did not slide smoothly from one orbit to another. They teleported, in a sense, from one state to the next. This stunned many because such behavior seemed impossible under classical rules. Yet nature did not ask for permission to break those rules. It had been doing so all along. It simply waited for someone like Bohr to discover it. As scientists explored the consequences of quantized energy levels, they uncovered patterns that Bohr's model predicted with remarkable accuracy. Hydrogen's emission spectrum, which had puzzled researchers for years, suddenly made perfect sense. Each colored line represented a jump between specific energy levels. By calculating these jumps, Bohr reproduced those lines exactly. This was more than a coincidence. It was a revelation. Bohr had found the blueprint of the atom's architecture, and by doing so, he had cracked open a door to a world far stranger than anyone expected. His equations answered one riddle after another, and each answer opened a pathway to more daring questions. Many physicists were astonished that Bohr's radical idea did not collapse under scrutiny. Instead, it grew stronger with every new observation. Even Albert Einstein, though skeptical of quantum leaps, respected the power of Bohr's model. Einstein preferred smooth continuity, but Bohr demonstrated that the universe had its own rules beneath that smooth surface. Every atom, every electron, every photon followed a silent language of quantized structure. Bohr had not just proposed a theory, he had uncovered a hidden order of reality. Yet, in the spirit of scientific progress, Bohr knew his model was not perfect. He recognized that while it worked beautifully for hydrogen, it struggled with more complex atoms. But instead of hiding these limitations, Bohr embraced them. He knew that science thrived on questions, not just answers. The model's flaws were not failures, they were signposts toward the next great ideas. He encouraged other physicists to challenge his work, refine it, and expand it. In this way, his concept of discrete levels became a foundation for future breakthroughs rather than a final solution. Werner Heisenberg, one of Bohr's most talented collaborators, took the notion of discrete energy states and transformed it into an entirely new mathematical framework. He created matrix mechanics, the first full formulation of quantum mechanics, which directly embraced the idea that electrons do not follow classical paths at all. Instead, they exist in states that cannot be described with continuous trajectories. This revolutionary approach came directly from Bohr's vision. Without discrete levels, Heisenberg's theory might never have taken shape. It was as though Bohr had laid the stones, and Heisenberg built a grand structure upon them. Erwin Schrödinger, another brilliant physicist, later offered a wave-based explanation, but even his wave equation ultimately described the same quantized energy levels Bohr had introduced. Whenever Schrödinger solved his equation for hydrogen, the discrete states reappeared. Whenever Heisenberg calculated observable properties, the same quantized results emerged. All roads led back to Bohr's insight, proving that his intuitive idea was far more powerful than many had first realized. He had discovered something fundamental about nature that no alternative theory could escape. As quantum mechanics matured, the concept of discrete energy levels became essential to understanding everything from chemical bonding to the behavior of stars. In chemistry, the arrangement of electrons in shells and subshells determines how atoms combine, react, and form the substances that make up the material world. Without quantized levels, chemistry as we know it would collapse into chaos. Bohr's idea silently governs the entire periodic table, dictating why atoms behave differently, why elements form patterns, and why molecules hold together. Every reaction in nature, from photosynthesis in plants to respiration in animals, depends on electrons jumping between quantized states. These jumps release or absorb energy, powering the processes that sustain life itself. Bohr's concept also became essential in astrophysics. The light emitted by stars is produced through electron transitions in atoms. When astronomers study distant galaxies, they analyze the spectral lines of starlight. Those lines are fingerprints of the quantized jumps Bohr described. By reading them, scientists can determine the composition, temperature, and motion of celestial objects light years away. Bohr's work allowed humanity to decode the universe, turning starlight into a cosmic language we could finally understand. Without the idea of discrete levels, the universe would appear mute, but thanks to Bohr, it speaks clearly. Moving into the 20th and 21st centuries, technologies built on Bohr's discovery reshaped modern civilization. Laser technology is rooted in controlled electron transitions between discrete energy states. In lasers, electrons are pushed into higher states and then fall back in synchronized leaps, releasing identical photons that form a coherent beam of light. Lasers power precision surgery, fiber optic communication, barcode scanning, industrial cutting, and countless other innovations. Each of these relies on Bohr's idea of quantized transitions. Semiconductors, the heart of modern electronics, also depend on discrete energy bands. Computers, smartphones, satellites, medical devices, all rely on electrons moving between quantized levels in carefully engineered materials. Giant industries, global economies, and the digital age itself owe their existence to the foundation Bohr laid. Even quantum computing, still emerging today, works by manipulating discrete states in quantum bits. The future of technology is thus built upon the very leaps Bohr described more than a century ago. But beyond the practical applications and technological triumphs, Bohr's idea forced humanity to confront a deeper philosophical truth. The universe is not continuous in the way our senses perceive it. Beneath the surface of experience lies a world built from quantized pieces, discontinuous events, and probabilistic behavior. Bohr revealed that nature is both orderly and unpredictable, structured and mysterious. His discrete energy levels became a symbol of this duality, a reminder that the universe cannot be fully captured by everyday intuition. Bohr embraced this philosophical depth. He believed that scientific theories were not absolute descriptions of reality, but tools for understanding. Quantum leaps, to him, were not just mathematical constructs. They were insights into the limits of human perception. He urged scientists to accept that the atomic world operated on principles that did not align with classical expectations. Instead of resisting this strangeness, he encouraged them to explore it with curiosity and humility. This attitude shaped the development of quantum mechanics and influenced generations of thinkers. As time passed, Bohr's concept remained unshaken. New experiments confirmed the existence of discrete energy states with astonishing precision. Many modern techniques, such as spectroscopy, electron microscopy, and quantum optics, rely on observing these quantized transitions directly. Bohr's idea has been tested in countless ways, and it has always survived, always emerged stronger. It became one of the most reliable truths in science, a pillar upon which modern physics firmly rests. Even today, scientists uncover deeper layers of quantization. In particle physics, quarks and leptons obey similar principles. In solid-state physics, electrons behave collectively in quantized ways that create exotic states of matter like superconductors and topological insulators. Everywhere researchers look, they see the fingerprints of Bohr's discovery. Discrete states are not just features of atoms. They are woven into the fabric of the universe. As we reflect on the impact of Bohr's insight, it becomes clear that the idea of discrete energy levels was not merely a step in scientific development, but a transformation in human understanding. It reshaped how we perceive matter, energy, and the rules governing reality. It created a bridge between theory and experiment, between the seen and the unseen, between the world we know and the world that exists beneath it. Bohr opened a door to the quantum realm, and through that door, scientists have walked for more than 100 years, discovering wonders that continue to astonish and inspire. Every quantum leap, every spectral line, every technological innovation rooted in electron transitions is a living tribute to his genius. His idea continues to shape the world, not as a relic of the past, but as a guide for the future. In the grand tapestry of scientific history, few insights have carried as much weight or spread as far as the concept Bohr introduced. It stands as a testament to the power of imagination, the courage to challenge established rules, and the ability to see beyond the visible into the realm where the universe quietly writes its secrets. And every time an electron leaps from one state to another, releasing a photon that travels through space, it echoes the profound simplicity and beauty of Niels Bohr's vision. Niels Bohr's ability to merge classical physics with early quantum ideas stands as one of the most remarkable achievements in the history of science. At a time when physics found itself split between the comforting predictability of classical laws and the strange, unsettling hints emerging from quantum observations, Bohr became a bridge between two worlds that seemed impossible to combine. Scientists were witnessing experimental results that defied traditional explanations. Energy behaved in discontinuous jumps, spectral lines appeared in precise patterns, and atoms refused to conform to the smooth, mechanical logic that had guided physics since the era of Newton. Many researchers recognized these strange clues, but could not reconcile them with the classical framework. Bohr, however, understood that the answers would not lie in abandoning classical physics, but in reshaping it to include the new quantum discoveries. Bohr recognized that classical models of the atom were fundamentally unstable. According to classical electromagnetic theory, electrons orbiting a nucleus should radiate energy continuously, spiral inward, and collapse the atom within fractions of a second. Yet atoms clearly existed in stable forms everywhere in nature. This contradiction revealed a flaw in classical assumptions, but did not offer a clear replacement. Bohr saw an opportunity here, a way to combine the structure of classical orbits with the newly emerging idea of quantized energy. Instead of rejecting classical mechanics outright, he modified it with a bold yet simple proposal. Electrons could occupy only certain allowed orbits, each with a fixed energy, and these orbits did not radiate energy. Classical motion still existed, but it was now restricted by quantum rules. This hybrid approach was revolutionary because it allowed Bohr to explain the stability of atoms while still holding onto familiar physical concepts. It was like building a bridge across a canyon, classical physics on one side, quantum ideas on the other, and Bohr constructed the pillars that connected them. In doing so, he provided a model that scientists could understand intuitively while also embracing the strange behavior revealed by experiments. The success of Bohr's approach demonstrated that combining frameworks was not a sign of weakness, but a powerful strategy in scientific progress. One of Bohr's most impactful achievements in merging these two domains was his explanation of the hydrogen spectrum. Classical physics had no answer for why hydrogen emitted light at specific wavelengths, but Bohr's model, using classical orbits restricted by quantum rules, predicted those wavelengths exactly. This was not mere coincidence. It was a triumph that proved quantum ideas could work hand in hand with classical mechanics in a coherent way. The scientific community took this as a sign that they were entering a new era, one where classical laws could no longer stand alone, but still had value when properly fused with quantum insights. This merging also influenced the philosophical direction of physics. Bohr understood that neither classical nor quantum descriptions alone could fully capture the behavior of nature. Instead, both were necessary, each offering a different perspective on reality. This idea later evolved into Bohr's principle of complementarity, the idea that light and matter could behave both like waves and particles, depending on how they were observed. His early blending of classical and quantum thinking laid the foundation for this deeper philosophical understanding, which would become central to the interpretation of quantum mechanics. Bohr's influence extended to the next generation of physicists who developed quantum mechanics into a complete and powerful theory. Werner Heisenberg, inspired by Bohr's willingness to challenge classical assumptions, created matrix mechanics, which abandoned classical paths altogether but retained the idea of quantized states. Erwin Schrödinger, though critical of some aspects of Bohr's thinking, still built upon the quantized structure Bohr introduced. Even Einstein, despite disagreements, recognized Bohr's brilliance in finding ways to merge seemingly incompatible ideas. The importance of Bohr's synthesis cannot be overstated. It showed scientists that progress often requires bold combinations, not strict loyalty to old principles. His model served as a stepping stone, guiding the world from classical certainty into quantum mystery. Without Bohr's bridging of classical and quantum concepts, the development of modern physics would have been far slower and far more chaotic. Today, the echoes of Bohr's merging are felt in every branch of physics. Quantum mechanics has replaced classical physics at microscopic scales, but classical laws still apply beautifully to the macroscopic world. The harmony between these two realms, often taught in classrooms, used in technologies, and applied in research, can be traced back to Bohr's insight. He showed that science does not move forward by discarding the past, but by building upon it, reshaping it, and harmonizing old ideas with new discoveries. His work remains a shining example of intellectual creativity and scientific courage. Niels Bohr's model found its most striking vindication when applied to the simplest atom of all, hydrogen. For decades, physicists had recorded the peculiar patterns of light emitted by hydrogen when it was energized. When hydrogen gas glowed, it did not produce a smooth rainbow, but a series of discrete, well-defined lines of color. These spectral lines appeared at very specific wavelengths, and each experiment repeated the same pattern. That fact alone told scientists that atoms emit light in certain fixed energies. Yet no existing theory could explain why these particular colors emerged, or why so many others were conspicuously absent. The classical view of electrons orbiting freely around a nucleus, radiating energy continuously, offered no hope of explaining why hydrogen would emit only those specific frequencies. It failed completely. Bohr's planetary model, combined with quantized energy levels, offered the breakthrough. Bohr proposed that the single electron in hydrogen could occupy only certain allowed orbits around the proton, each orbit corresponding to a fixed energy level. When an electron jumped between these levels, for example, dropping from a higher level to a lower one, it would emit light whose energy precisely matched the difference between those two levels. That energy, converted to frequency, determined the color, or equivalently, the wavelength of the emitted photon. In this manner, Bohr transformed the mysterious spectral lines into predictable outcomes of a mathematical model. These were not random emissions, but structured, quantized transitions dictated by physical laws. What had seemed almost magical, an atom producing particular colors, became logical, calculable, and ultimately understandable. When Bohr worked out his calculations, he discovered that his predicted wavelengths matched the experimentally observed spectral lines of hydrogen with remarkable precision. Each line in the measured spectrum, red, blue-green, violet, ultraviolet, corresponded to an electron transition between definite energy levels in Bohr's atom. The agreement was not rough or approximate, it was strikingly accurate. For many physicists, this was the turning point. It demonstrated that the atom was not an inscrutable black box, but a system with an internal architecture open to human insight. The elegant match between theory and observation gave Bohr's model legitimacy and power. It showed that the concept of quantized orbits was not a mathematical trick, but a representation of how nature actually behaves at microscopic scale. Because hydrogen is the simplest atom, one proton, one electron, it served as the perfect test. If Bohr's model could not explain hydrogen, it had no chance of explaining more complex atoms. But the model did succeed. The fact that the simplest atom obeyed Bohr's predictions suggested that deeper laws governed all matter. Suddenly, the periodic table, chemical behavior, and atomic interactions gained a solid physical underpinning. The spectral fingerprint of hydrogen was no longer a curiosity. It became a cornerstone of atomic theory. The precision of Bohr's explanation also made the model enormously practical. Spectroscopy, the study of light emitted or absorbed by matter, emerged as a powerful tool to investigate atomic structure, chemical composition, and even astronomical phenomena. Scientists could analyze light from distant stars and deduce which elements they contained, simply by comparing observed spectral lines with those predicted by theory. The spectral lines of hydrogen, helium, and other elements revealed the composition of celestial bodies, the behavior of gases in stars, and the dynamics of cosmic phenomena. Bohr's success with hydrogen thus paved the way for a new form of observational science, one that looked at the universe not in shapes or motions, but in discrete patterns of light. Beyond pure science, Bohr's accurate predictions fostered confidence in quantum ideas. If a simple atomic model could explain real experimental data so well, perhaps the quantum realm, strange, counter-intuitive, seemingly mystical, was exactly where physicists needed to focus. Classical physics, with its continuous energies and smooth motions, could no longer claim to describe all of reality. The success of Bohr's model with hydrogen gave quantum theory legitimacy. It showed that quantization, far from being a mathematical curiosity, was a fundamental characteristic of nature. Yet Bohr was aware that his model did not offer a complete picture for all atoms. He knew that the simplicity of hydrogen made it uniquely suitable for his approach. Multi-electron atoms presented complications that his original model could not handle elegantly, but the fact that hydrogen behaved so beautifully under his rules meant that the foundation was correct. Later refinements, probability waves, electron orbitals, quantum numbers, and more intricate mathematics would build on that foundation. Bohr's explanation of hydrogen's spectrum remained the first solid proof that quantum rules applied to real atoms, not just theoretical abstractions. In classrooms, textbooks, and lectures around the world, students encountered the hydrogen spectrum as the first evidence of quantum mechanics. The colored lines, once mysterious and mystical, became legible. They represented quantized transitions, the hidden architecture of atoms, and the power of human thought to unveil nature's secrets. The match between Bohr's predicted values and empirical measurements stood as a shining example of how theory and experiment can come together to illuminate reality. The importance of this achievement cannot be overstated. By explaining why hydrogen emitted only specific spectral lines, and predicting exactly which ones, Bohr had given science its first reliable atomic model. He had transformed atomic spectra from odd phenomena into tools of understanding. He showed that atoms are not chaotic swirls of particles, but organized, rule-governed systems. He demonstrated that energy in atoms is not infinitely variable, but quantized. And most importantly, he gave humanity a way to read the language of light, a language that atoms use to communicate their structure. In doing so, Niels Bohr laid one of the deepest and most enduring foundations of modern physics. Niels Bohr's influence reached far beyond the equations and models he created, for he was not only a scientist seeking answers, but also a thinker determined to understand what those answers meant. As quantum theory matured, Bohr became one of its most powerful philosophical architects, shaping the way physicists interpreted this new and unsettling vision of the universe. At a time when quantum mechanics seemed to defy logic, intuition, and centuries of classical thinking, Bohr stepped forward to offer a deeper understanding that the strange behavior observed in quantum realm was not a flaw in the theory, but a feature of nature itself. He helped the scientific world come to terms with a reality where certainty dissolves, where probabilities rule, and where observation changes the very phenomenon being observed. Bohr understood that quantum mechanics was more than a set of mathematical tools. It was a profound shift in how humanity viewed the universe. Classical physics had presented a world of clear causality, predictable outcomes, and objective properties existing independently of measurement. The quantum world shattered this comfortable picture. Electrons behaved like particles in one moment and waves in another. Their positions and momenta could not be known simultaneously with unlimited precision. Photons could pass through two slits as if they traveled multiple paths at once. For many scientists, these discoveries were unsettling, even absurd, but Bohr embraced them with calm clarity. He believed that nature was not required to obey human expectations, and the task of scientists was to interpret new evidence with an open mind. This mindset led Bohr to articulate the philosophical principles that became central to quantum mechanics. One of his most influential ideas was the conviction that classical concepts were still necessary for describing measurements, even if quantum behavior defied classical intuition. In other words, while electrons and photons behaved in ways classical physics could not fully describe, the instruments used to measure them still had to be explained in classical terms. Without classical language and classical reference frames, scientists could not even define what they were observing. This blending of perspectives helped physicists navigate the tension between the old and the new, the familiar and the strange. Bohr also recognized that many of the paradoxes of quantum mechanics arose from attempts to force quantum phenomena into classical categories. He encouraged scientists to accept that quantum objects could not be fully described by traditional concepts like position, trajectory, or shape. These concepts worked well in the macroscopic world, but became inadequate at atomic scales. Instead of resisting this insight, Bohr urged physicists to expand their conceptual toolbox and adopt new ways of thinking that matched nature's behavior, not their expectations. This philosophical flexibility allowed quantum theory to grow into a complete and consistent framework despite its counterintuitive nature. Even before Bohr formulated his famous principle of complementarity, he had already begun shaping the philosophical foundation on which that principle would stand. He believed that quantum mechanics required a shift in perspective. Scientists had to accept that the act of observation played a central role in shaping outcomes. This was not because human consciousness interfered with nature, but because the experimental setup itself determined which aspects of quantum behavior could be revealed. Bohr argued that reality at the quantum level was not fully separable from the methods used to examine it. This insight helped to solve many apparent contradictions in early quantum theory and provided a coherent way to understand experiments that seemed impossible to explain with classical logic. Bohr's willingness to explore these philosophical implications made him a central figure in the debates of his time. Scientists like Einstein challenged quantum mechanics with thought experiments designed to highlight its paradoxes, but Bohr repeatedly responded with explanations grounded in the philosophical structure he had helped build. His interpretations did not rely on hidden forces or unobservable mechanisms. Instead, they accepted the quantum world on its own terms. This clarity of thought supported generations of physicists as they applied quantum principles to new problems, from atomic structure to nuclear physics and beyond. The significance of Bohr's intellectual contributions can be measured not only by the theories he helped refine, but by the mindset he inspired. He taught scientists to embrace uncertainty, to accept that the universe might operate according to rules unlike anything experienced in daily life. Under his influence, quantum mechanics became not only a mathematical description of nature, but a new philosophy of reality. Today, this world shapes how physicists understand the smallest scales of existence, showing that Bohr's role in defining the philosophical roots of quantum theory remains one of his greatest legacies. As quantum mechanics expanded beyond the early atomic models, Niels Bohr found himself not merely contributing theories, but guiding an entire generation of scientists through the conceptual storm that quantum ideas unleashed. He became the mentor, the interpreter, and often the philosophical anchor for young physicists wrestling with a world where classical intuition broke down. Bohr understood that quantum mechanics demanded a new kind of thinking, and he took it upon himself to cultivate that mindset in those who worked with him. His institute in Copenhagen soon became the intellectual center of this new scientific revolution, a place where the brightest minds gathered to debate, argue, calculate, and rethink the very foundations of reality. Bohr's influence on the early architects of quantum mechanics cannot be overstated. Young scientists who later became giants, Werner Heisenberg, Wolfgang Pauli, Leon Rosenfeld, and others, found in Bohr not just a teacher but a guiding presence. He encouraged creativity while insisting on rigorous thought. He challenged assumptions but welcomed bold ideas. His conversations, often long and philosophical, pushed his students to confront the deeper implications of their work. Many recalled how he would pace the room slowly, speaking in incomplete sentences, forcing them to think alongside him, to fill the conceptual gaps themselves. In this way, he built not just theories but thinkers. Heisenberg's discovery of matrix mechanics was deeply shaped by his time with Bohr. The two engaged in intense discussions, sometimes lasting late into the night, exploring the meaning of measurement, uncertainty, and the structure of atomic phenomena. When Heisenberg formulated his uncertainty principle, Bohr helped him understand its philosophical importance, integrating it into the broader framework of quantum mechanics. Their close collaboration, which oscillated between agreement and gentle conflict, produced some of the most important conceptual foundations of the theory. Heisenberg often said that working with Bohr was like playing chess against a grandmaster who taught you the strategy as you played. Wolfgang Pauli, known for his sharp intellect and even sharper criticisms, also benefited from Bohr's patient and reflective style. Pauli's exclusion principle, essential to understanding the structure of multi-electron atoms, emerged from an intellectual environment shaped by Bohr's influence. Though Pauli was famously blunt, Bohr treated him with warmth and respect, recognizing that his brilliance needed space to grow. Their exchanges helped refine some of the most complex ideas in quantum theory, blending Pauli's mathematical precision with Bohr's philosophical clarity. Bohr's Institute became a crossroads for scientists across Europe and beyond. Students, postdocs, and established researchers traveled to Copenhagen because they knew that Bohr fostered an environment unlike any other. It was not simply about solving equations or performing calculations. It was about understanding what those equations meant, what they revealed about the nature of reality. Visitors recalled the unique combination of scientific rigor and philosophical depth that permeated discussions there. Ideas were not rushed. They were explored, dissected, challenged, and rebuilt. This atmosphere allowed quantum mechanics to evolve into a coherent and unified framework, rather than a patchwork of disconnected discoveries. As quantum mechanics matured, Bohr's role shifted further toward providing conceptual guidance. He helped physicists understand not only how the mathematics worked, but why it worked. He provided context, interpretation, and meaning. When disagreements arose, whether between Heisenberg and Schrödinger, or between Einstein and nearly everyone else, Bohr was often at the center, mediating discussions and offering insights that drew connections rather than deepened divides. His strength was not in providing final answers, but in reshaping questions so that answers could emerge naturally. One of Bohr's greatest contributions as a guide was his insistence that quantum mechanics needed a consistent interpretive framework. Without this, he believed, the theory would remain a mathematical tool rather than a true explanation of nature. His later principle of complementarity grew directly out of these interactions with younger physicists, but even before he articulated it fully, he shaped the way others thought about wave, particle, duality, measurement, and the limits of classical description. His guidance created the intellectual soil from which the full structure of quantum mechanics eventually grew. By nurturing the next generation, Bohr ensured that quantum mechanics would not remain the work of a few isolated thinkers, but would become a shared intellectual achievement. He taught his students to question deeply yet reason clearly, to embrace paradox yet seek coherence. Through this mentorship, he amplified his influence far beyond what he could accomplish alone. His students became leaders, his institute became a beacon, and his ideas spread not only through papers, but through minds shaped by his teaching. In this way, Niels Bohr became more than a contributor to quantum mechanics. He became one of its architects at the human level, building the community, the conversations, and the conceptual foundations that defined the field for generations to come. The final keynote centers on how Niels Bohr's legacy continues to shape the modern world, not merely as a chapter of scientific history, but as a living, breathing influence woven into the fabric of today's technology, philosophy, and global collaboration. Bohr's ideas were never confined to the early 20th century. They were seeds planted in the soil of a rapidly advancing world. As decades passed, those seeds grew into branches that reach every aspect of contemporary physics, from the computers we use to the way humanity approaches complex truth. His legacy is not simply that he built quantum theory, but that he built a way of thinking, one that encourages humility before nature, a willingness to embrace paradox, and the courage to challenge our deepest assumptions. The most visible continuation of Bohr's influence lies in the technologies that underpin the modern digital age. Every transistor, every microchip, every logic gate inside your phone or computer rests on quantum principles that Bohr helped define. The very concept that electrons occupy discrete energy levels formed the basis for semiconductor engineering, making possible the leap from vacuum tubes to integrated circuits. Whenever information is stored, processed, or transmitted, the quiet echo of Bohr's early debates with classical physics is present. Without his explanation of atomic structure, the electronic revolution would have remained an impossible dream. And as the world enters the era of quantum computers, machines that exploit superposition and entanglement to perform calculations, once thought unimaginable, Bohr's philosophical approach becomes even more crucial. The Copenhagen Interpretation, with all its nuance and restraint, still shapes how scientists interpret the strange behavior of qubits. Even in cutting-edge laboratories, researchers often find themselves returning to the foundational questions Bohr raised more than a century ago. But Bohr's legacy is not solely scientific or technological. It also extends to the philosophical world of the modern age. His principle of complementarity, which suggests that opposing descriptions can both be true depending on the context, has influenced fields far beyond physics. Psychologists, biologists, and even political theorists have invoked Bohr's insights to understand complex, contradictory systems. The notion that reality may not always submit to a single, absolute narrative resonates deeply with contemporary society, where perspective, context, and uncertainty shape almost every major discussion. Bohr's work invited the world to rethink the idea of objective truth, not by denying it, but by demonstrating that truth can appear differently when viewed through different lenses. This was not relativism. It was a profound recognition that nature itself is multifaceted. Another major part of Bohr's modern relevance lies in his humanistic spirit. He believed that open communication, shared knowledge, and international collaboration were essential for the progress of civilization. After witnessing the devastation of 2 world wars, he argued passionately for global scientific cooperation. During and after World War II, he advocated for transparency in nuclear research, urging world leaders to prevent secrecy from fueling destructive arms races. Though not all his warnings were heeded, the modern scientific community's emphasis on international partnerships open-access journals, and cross-border research owes much to Bohr's early vision. In today's world where global challenges like climate change, pandemics, and energy crises demand unified action, Bohr's belief that knowledge must transcend political boundaries feels more relevant than ever. His legacy also endures in the countless scientists he inspired. Many of the most influential physicists of the 20th century studied directly under him or were shaped by his ideas. Werner Heisenberg, Wolfgang Pauli, Leon Rosenfeld, and many others carried Bohr's intellectual DNA into their own groundbreaking discoveries. They extended and sometimes challenged his interpretations, but their work formed a continuous thread connecting the early quantum pioneers to the expansive research networks of today. Through his institute in Copenhagen, Bohr created not just a laboratory but a community, a place where ideas could collide, evolve, and grow. The collaborative atmosphere he cultivated has become a model for research institutions around the world. Even culturally, Bohr's presence can still be felt. His debates with Einstein have entered the realm of legend, symbolizing the eternal struggle between intuition and counterintuitive truth, between classical expectations and quantum reality. These discussions continue to inspire books, films, plays, and philosophical essays, reminding the world that science is not merely a collection of equations, but a human story filled with conflict, imagination, and wonder. In educational settings, Bohr's model of the atom remains one of the first scientific concepts that young students encounter, sparking curiosity and laying the foundation for deeper exploration. Though later refined by more advanced theories, Bohr's model survives because it bridges simplicity and accuracy, a testament to his ability to communicate complex ideas with clarity. Ultimately, the continuing relevance of Niels Bohr's legacy lies in his unique blend of scientific rigor, philosophical depth, and human empathy. He recognized that understanding nature required not only sharp intellect, but also humility. He challenged the world to accept uncertainty not as a failure of knowledge, but as a fundamental feature of existence. And perhaps most importantly, he demonstrated that science is a collective endeavor, one that grows when people share openly, think boldly, and remain willing to question even their most cherished beliefs. In an era increasingly shaped by quantum technologies, global interdependence, and philosophical complexity, Bohr's voice continues to guide, inspire, and remind us that the universe is far more mysterious and far more beautiful than we can imagine.